Okay, question 65. A typical laboratory centrifuge rotates at 4,000 RPM. Test tubes have to be placed into a centrifuge very carefully because of the very large accelerations. What is the acceleration at the end of a test tube that is 10 centimeters from the axis of rotation? So, the first thing we want to take into account is the information that we're being given initially, which is that the object is going to be rotating at 4,000 RPMs. Now, this is not the ideal set of this is not the correct labeling that we want to do for this problem. So we need to convert rotations per minute into radians per second. And so we can use this equation for angular speed to basically turn this into the proper form that we're going to need in order to solve this, so that it can properly function with the equations that we're going to be using for later. So we know that 360 degrees equals 2 pi radians. And then we also know that we need to convert this from minutes to seconds. So we will divide this by 60. So we have 4,000 units times 2 pi radians over 60 seconds, which will give us a answer of about 418.87902 radians per second. And so now we have it in the correct form. And so now what we're going to do with this new form is plug it into this equation that will find the centrifugal acceleration. And so what this will basically do is, excuse me, is that this will tell us the acceleration of the element at the end of its radius here. Because we've just calculated how many times it rotates per second. So that could rotate 418 times here or here. But its acceleration or magnitude of its acceleration could totally be different if it's here or here. And that's why we're trying to figure this out. So our angular speed, which we're going to represent as W, just any letter just to represent it, and we will square that and multiply by the radius, which makes sense because the radius will dictate the amplitude of the acceleration. But before we can do this, the only thing we're given is 10 centimeters. This was an error. This is supposed to be 10 centimeters. My apologies. But the radius is 10 centimeters. But we need to convert that into meters to properly function, or else we will get an incorrect answer. So we have to convert it to meters, which is 0.1, and then we will square 418.8 by 0.1, which will leave us with 17,545.96 meters per second squared. And that is the centrifugal acceleration as it is revolving around this 10 centimeter area at 4,000 RPM. And then the second part, for comparison, what is the magnitude of the acceleration a test tube would experience if dropped from the height of 1 meter and stopped in a 1 millisecond long encounter with a hard floor? So this is going to concern gravity, also regarding the height, and we are going to take into account the collision time. And so in this particular case, the impact time is going to last 0.001 seconds. And so the quicker the impact time is, the faster the acceleration has to change from what it is while gravity is acting upon it until its final stop. So we will calculate this final velocity right before it makes contact, before impact, with this equation, which is the square root of 2 times gravity times the height. So we want to find the velocity right before impact, and then use the impact time to see how fast it goes to 0. And so we calculate that out, and the velocity is 4.427 meters per second. Now we use this to find the acceleration. We know that it's going from 4.42720. So that is our delta V. And our change in time, as we know, is 0.001 seconds. Plug that in there, and we get 4,427 meters per second squared. So this object has an acceleration of 4,427 meters per second squared in this impact time. So there is a tremendous amount of energy to stop it.